right? This is two sections, right? And it's a section which is giving us what they're calling parent functions. And the concept of parent functions is something that we had in Algebra 2 also. And then the transformations, which means how do you move those parent functions around by adding or subtracting numbers or putting minus signs in front or things like that. I mean, that's what this is all about. And like I say, it's, I would say if there's one part of this that might be different than what you did in this whole concept thing, it's using what they call non-rigid transformations. Because I think most of the time in Algebra 2, we don't actually multiply the parent function. We add, subtract, and put minus signs in there. But there are going to be a couple things that are it's in this first section, which I'm not 100% sure why they put them in that section, but they're things we're supposed to know. One of them is part of actually what you're being quizzed on today, but somehow it shows up here again too. These are what they call parent functions, right? And the first two, this is a constant function. A horizontal line is a constant function. It just means that the y value is constant. It never changes, right? This is the identity function, and it means that the x and the y values are identical, right? If it's 0, 0, 1, 1, 2, 2, and all the points in between, right? Every point on the line, the x and y coordinates are the same. These are considered linear functions, right? There is, other than that, there isn't like one linear function that you could say, but these are definitely linear functions. I mean, you could make a case that absolute value is linear, but it's really not because it's got two pieces to it. You know, absolute value is really a piecewise function, right? It's defined on the left by this function, y equals negative x, negative slope. It's defined on the right, y equals positive x. That's piecewise defined. So the other what they call parent functions include the square root, the quadratic, right, which we're familiar with that, cubic. This is called they're calling it a reciprocal function. If you had it in Algebra 2, they might have called it inverse variation. It was at the beginning of the rational functions, but it's 1 over x. And then this is kind of an odd function, which they're calling greatest integer function. But if you just look at what it looks like, it's also called a step function. And you could actually do that one in your calculator, right? You can go to math, and I think it's over on that one right there, math num integer. That is the greatest integer function. Basically means that you have the same value of y for all values of x in between 0 and 1, right? And then when you get to 1, it jumps up and it increments by a little bit. I mean, this could be, I don't even know, cell phone usage or something where you get charged for each, 100 minutes more that you use, right? You get charged the same thing up until you get to that next increment, and then the price goes up, right? It's not a straight linear graph. It just goes in steps. So these are what they call the common functions. And this comes from the first section, P.7. Okay. Now, the problems that we're going to do out of P.7 are actually not the transforming yet. That'll come in section P.8. There's two kinds of problems we end up doing in the P.7. And the example is this, and there's a couple homework problems from this. Now, it says write a linear function, and then it gives us these two function values. If you remember, in the section that we did, which was about, it said linear equations in two variables, right? If we were given 2 points, we were supposed to be able to come up with the equation of a line. Well, that's what they've given you here. That's just 2 points. It's another way to say you've been given 2 points, -2, 6, and 4, -9. Right? How is it that you take 2 points, and make the equation of a line. Do you remember? Remember what the first step was? Connor? I mean, what's the only thing we can do with 2 points? Slope. You calculate the slope, right? So first step is calculate a slope. M equals negative 9 minus 6 over 4 minus negative 2, which is negative 15 over positive 6, which is negative 5 divided by 3. Negative 5 over 2. Okay. Once we had a slope, what did we do with the slope? How? Plug it in to what? To this. Right? Point slope form of a line. So now we're going to plug in. The negative 5 halves is the slope. We need to plug in for 1 point, x1, y1. You've got 2 choices. Take your pick. It does not matter which one you pick. I'll pick the first one just because it's first. So it'll be y minus 6 equals negative 5 halves x minus x plus 2. Solve for y. Right. Y minus 6 is negative 5 halves x. And what do we get when we multiply negative 5 halves times 2? How about minus 5? Right? The 2's cancel. And then you have to add 6 to both sides. Y equals negative 5 halves x plus 1. So that's how you take 2 points and make a line. Whether it's given like this or whether it's given like this, it's still all you're being asked to do. Again, you know, this is the example in the book. It's probably the one, there's usually like an example, and then underneath there's like a check for understanding. It's probably the check for understanding. So you've got their example too, above that. You know, if you're doing the homework you don't understand, you should look at the examples or bring up the video, watch what I did. Okay, then we graph piecewise functions. I mean, that's the other thing that's in this section, P.7, which I don't really find much in common with the library of common functions or parent functions. But remember, a piecewise function is where you define the function in different ways, depending on what x values you're going to plug in. So in this first one, you're going to use this expression right here when x values are less than or equal to negative 4. You're going to use this expression if the x values are greater than negative 4. So, I mean, what we've already done with this is we've evaluated piecewise functions. If I said find f of 3, right, which one of these functions would you use to calculate f of 3? Ariel? The second one, because 3 is greater than negative 4, right? So you would plug it in here, 3 plus 5, 8, right? If I said find f of negative 10, you would say, well, negative 10 is less than or equal to negative 4. I'm going to use this one, right? So when you evaluate piecewise functions, this is domain, right? To use the domain to figure out which function, which expression you're going to use, plug it in, and you've got your answer. But what you don't want to do is plugging it in both. If you plug it in both, then clearly you don't get the concept at all, right? So don't plug it in both. Pick the right one. Now, when we graph these, right, if I graph negative 1/2 x minus 6, I mean, both of these are straight lines, right? This is a straight line that has the y-intercept of negative 6, has a slope of negative 1/2. So it would look like this. Let me do it in, that'll be good. Blue's fine. So it's got a y-intercept of negative 6, 2, 3, 4, 5, 6. And it's got a slope of negative 1/2, which means up 1 over 2, like that. That's negative 1/2. And I can even make that go down there. Right? This thing has a graph with a y-intercept of 5 and a slope of 1. So start at 5, 1, 2, 3, 4, 5, and a slope of 1. That would make it look something like that. Now, if I was looking at both of those lines together, that they described one graph, would you say that it's a function? Would it pass a vertical line test? Could I cross this graph in more than one spot with one vertical line? I sure could, right? That means it wouldn't be a function, right? And these are functions. They're piecewise defined functions. So what you got to be careful of, we are not graphing the lines everywhere. We're only graphing this line for x less than or equal to negative 4. So let me take that line right here, the first one, and I'm only going to have it start at negative 4. 1, 2, 3, 4. And now I'm all messed up because of, okay, 2, 4, 6. So it should have gone there, it should have gone about like that. Okay. And the other one should have started, where's the, that's the wrong one. There we go. The other one should have started at negative 4. So it's about here. And then because this one said less than or equal to negative 4, then that means that should have been a filled in circle. Because this one said greater than negative 4, that should have been an open circle. That's what a piecewise function looks like, right? You never want to draw the graphs, both graphs, like over each other. They're never going to be over each other, right? Because it wouldn't be a function if it was. So just, here's your dividing line, negative 4, graph one of them to the left, one of them to the right. Now, you can do that in the calculator, right? I can show you how you can do that in the calculator. If you go to the y equals, right, clear. On the first line, I'm going to put this function, okay? Put it in parentheses. So in parentheses, negative 1/2 x minus 6. I'm going to say negative x divided by 6 minus 6. No, divided by 2. That was wrong. Divided by 2 minus 6, right? End parentheses. Then you do a divide symbol, and then you put in the x less than or equal to negative 4. So do another set of parentheses, and x, and now we have to remember, where do you get those inequality symbols in the calculator? Second math, right? Second math. And the greater than or less than or equal to, number 6. And that was negative 4. End parentheses. So it should be the function in parentheses, divide the domain in parentheses. Then you go down to the next line, right? In parentheses, x plus 5. That's easy. X plus 5. End parentheses, divide. And now we want to say x is greater than negative 4. X, second math, test menu. Greater is number 3, and negative 4. And now we hit the graph. Let me get a different zoom. Zoom 6. So it draws that one only to the left of negative 4. It draws that one only to the right of negative 4. So, I mean, it's okay to do these in your calculator, but understand that if you're going to do it in the calculator and then transfer your answer to a quiz or a test or something like that, you got to give me enough detail, right? Don't make it just like lines that aren't really clear where they are supposed to be. I mean, you could even then, like if you go to the table of values, this is the table of values for that. You know, you can evaluate. It'll give you the values from the function which is valid for that part of the domain. So those are the only two things we do from this P.7, right? Make a line given 2 points in the function notation, and then graph a piecewise function. And you got a way to do it in the calculator. Is everybody all right? Anybody try that and not get it? Okay, so now we're going to get into all the different ways that we transform functions. Let's see. The absolute value of x. Do we know what the shape of an absolute value function is? Instantly? It's a V, right? It's a V with the vertex at the origin. It opens up something like that. Okay. What does it do to the graph of that function if you subtract 2 from the x inside the function? Do you remember what the shift is? 2 to the right, right? If you're not clear on that, you could do a table of values or just put it in the calculator. Look at the graph of the absolute value of x minus 2 and see which way it goes. It goes to the right when there's a minus, which is kind of counterintuitive, right? We tend to think that it should go to the left because minus would be left, right? But when you put in the positive 2, that's what makes the function equal 0. And it hits the axis where the function equals 0. So positive 2 moves it to the right. And that's what this is saying here. When you have your shift of the minus c, that means to the right. If it was a plus, it would have been to the left. So inside the function, it's a horizontal shift. Minus means right, plus means left. Right. What does it do to the graph of the function if you add or subtract a number after the function? It's not a horizontal, is it? We already did that. It's vertical, right? Plus means up, minus means down. That's what this thing here. Plus c means up, minus c means down. So go up to, draw your graph. Right. All these together are all called rigid transformations. Rigid meaning they don't change the shape. They're just taking the same shape and moving it around like this. Are we good with that? Okay, what would be this is the parent function x to the third. What is the shift? Because we added 5 after the function. Because it's not inside the cubic, right? It's not x plus 5 in parentheses cubed. It's x cubed plus 5. What does that do to the graph? Up. Right? So that should have been up 5. Which basically means you should take every point on this graph, if you just moved it up 5 and then sketch a new graph. I mean, this is kind of accurate. I mean, 0, 0 is definitely on here. 1, 1 was on the parent function, and I moved that up. -1, -1 is on the graph, so I go up 1, 2, 3, 4, 5. And then this point, you know, -2, -8, if I move that up, it's about here. So I can draw that as a graph. Looks something like this. So just take the graph you're given, move it up 5. We good, Ariel? Okay. Okay. Graph using as transformations. Again, when they say transformations, that's what it means is don't do a table of values. Just understand the shape and move it according to what you see here. I mean, what are the transformations that we see here? Right 3, up 2. So you could take some specific points on this graph and just move them. Right 3, up 2. Like this point, 0, 0, move it right 3, up 2. Right? 1, 1, right 3, up 2. -1, -1, right 3, up 2. -2, -8, right 3, up 2. And sketch a new graph. All right, looks something like this. Right. Do you remember this stuff from Algebra 2? A little bit? Okay, reflections. Right, there are black here. I'm going to use the square root function now. If you remember from the very first slide where we had all the parent functions, the square root function has a general shape, right, like this. Okay, what does it do to the graph of a function when you put a minus in front of it? Say again? It's a the proper name is a reflection, but you might have called it a flip, right? Which way does it flip? Down, like that, right? Where a minus in front means flip it across the x-axis. So it'll look like this. Okay. Now, and you've seen that one before. I'm sure you've seen that one before. You probably didn't see the one that flips it across the y-axis, right? And that's when you put the minus inside the function in front of the x. And the reason I had to switch functions, because I like to do all these with absolute value. Absolute value is clean. You know, it's a really sharp angled V that you can actually see exactly what's going on. But if I take a V and I flip it across the y-axis, what does it look like? Same thing. Yeah, you wouldn't see anything, right? But at this one, if I start with the parent function and I flip it across the y-axis, it'll look like that. Right? So these are, right, this is reflect. The way the book says it, this is a reflection in x-axis. This one is a reflection. I hit that, I know I did. Reflection in y-axis. Would you consider those rigid? Are they distorting the shape at all? No, they're still rigid. Okay, so let's see. Let me go back to blue, back to thin. Okay. So what are the transformations you see in this first one? The minus in front is a reflection in the x-axis. The minus one inside is right. Right one. So we would draw it like this. Right one, and make it go down. What are the transformations you see inside? Okay, the minus in front of the x means reflect in the y-axis. The minus one means to the right. So we would be taking this thing and going. So minus one to the right, and then we reflect it in the y-axis so it goes the other way. And that's incorrect. What's incorrect about that? Can anybody see? Say it again. Okay, let's see. If I put in a 1 here, this is saying that the point here is 1, 0 should be on the graph. But what happens if I put in a 1? I would get -1, -1, -2. That is not right. And I make that mistake sometimes. We should really do this. Okay, we should really do this. We should go, make this in the parentheses, that's negative x plus 1. And now you see it for what it is, right? It's a left shift, reflect in the y-axis. Okay, try that again. And again, now if I plug in -1, -1 plus 1 is 0, square root of 0, 0. So that is the point that's on the axis right there. Okay, I think I'm down to the last kind of transformation. Like I said, everything we've done so far, you could have called rigid transformation. It does not distort the shape of the graph at all. Right? In this case, it will distort the shape of the graph, so it's called non-rigid. And we're starting out again with the absolute value function to be the parent function. And then we're going to first multiply the absolute value function by a number bigger than 1. We're going to use 2, right? And notice in this, where I've got the table of values, what does that do to the value of the function when I multiply on the outside times a number bigger than 1? Right? It took the 2, it made it a 4. It took the 1, it made it a 2, right? 0 stays the same, 1 goes to 2, 2 goes to 4. So if I looked at that on the graph, it would look like this, right? 2, 4. 2, 4. Right? That's not the same shape of a V that we had before, right? Now the slope of the line on the right is a 2. The slope of the line on the left is a -2. That's called a stretch. When you multiply by a number bigger than 1, that's called a vertical stretch. And probably if you see it in the back of the book, they're going to say a vertical stretch by a factor of 2. Right? That's how it gets worded. Vertical stretch. Okay, what does it do to the graph function if we multiply by a number less than 1? You know, every one of the y values gets cut in half. So what does it make the graph look like? It goes like like this. That's a very bad line, but right, it goes up slower as you go away from the origin. What do you think the word is they use for that? For when you multiply by a number less than 1, if bigger than 1 is called a stretch, what word do you think we would use for less than 1? Shrink. This book calls it a shrink. The New Algebra 2 book calls it a compression. Okay, vertical shrink. And I'm trying to think. And just to be clear about that, I'm going to insert a page real quick, if you're done with this. Are we done with that? Caitlin? Mitch? Are you done? Okay. So let's insert page after. Right. What if we had this function? F of x equals -3 times the absolute value of x minus 4 plus 7. Right. What is the minus 4 doing inside? Right 4. Okay, that's the right 4. What is the plus 7 afterwards doing? Up 7. Right? What does the negative do in front of it? A minus in front is a flip, right? Flip across the x-axis. And then, would you consider that a stretch or a shrink? It's being multiplied by, what would you call that? It's a stretch, right? In your, really when we talk about the multiplier, we're supposed to use absolute value, but just try to separate out the minus from the number. If there's a minus there, don't say, well, -3 is less than 1, therefore it's a shrink, right? No, it's still a stretch. Consider the negative to be the part that flipped it, and the 3 is a stretch. It's just stretching it in a downward direction. So this is still a stretch. Okay. And that is it. I think. I can check. Okay. Linear, piecewise functions, parent functions, shifts. There's homework from the 2 different pages.